All right. Good morning, everyone. So we'll start from where we left yesterday. Yesterday we were talking about the spacing requirements, right? So there were restrictions on how close and how far away the consecutive bolts can be. Agreed? You can hear me, right? And you can see the screens as well. Fine. So as you may remember, the absolute maximum distance between the two consecutive bolts was specified as 32 times the thickness of the plate, or that is the thinner plate. Okay, here. And minimum of that and 300 millimeters. And that was in any direction. So that could be in the direction perpendicular to the loading direction. So for example, these three values, these are, so the spacing between this bolt and this bolt should be less than 32 T or 300, whichever is less. But it should also be greater than 2.5 D, which is specified here. Okay, and D is actually the bolt diameter, correct. So now,
Sir,
yes,
this maximum spacing conditions were only for bearing or all type of bolts.
is it only for bearing or all the?
Why? Because the stress concentration comes only in bearing.
No, so this is not only for stress concentration requirement. There are three requirements, right? The space for tightening, overlapping. So the minimum requirement of 2.5. So that is how close they can be. That is because of all three reasons, right? So it is not purely by bearing requirement consideration.
Yes.
Right. So that's why this 2.5 D is minimum require. That is the closest you can get between the two bolts, irrespective of what types of bolts these are.
Yes.
Maximum spacing, that cannot be more than 32 T or 300 mm, whichever is small. And in addition to that, in the direction of the load, the requirements are more stringent. So the bolts cannot be farther than 16 times T and 200 mm if the load is in tension, and even more stringent if the load is in compression. For compressive loads, you have a requirement of your bolts cannot be more than 12 times T away from each other. Yeah, for them to be considered a part of the same joint. So if these two bolts are to be considered as a single joint, when I consider them as single joint, I assume that, for example, if I'm applying, let's say only these two bolts are there, and I'm applying any load on the joint, then if I want to assume equal distribution between these two bolts, then I have to keep the distance between these two less than 12 T. Otherwise, what will happen is that I'll have to consider this joint separately and this joint separately, and I have to consider the flexibility of the plate in between. Okay, and there is a risk of buckling of the plate. So because there is a compression involved, so what may happen is that if you have two plates, one plate going this way, the other plate going this way, when you have one bolt here, one bolt here, I'm applying compression, this there is a risk of this plate buckling here, right? So if the two joints are too far apart, then the plates may buckle. Also, so that will lead to uneven distribution of stresses. Similar thing will happen in tension, not buckling. In tension, it won't undergo buckling, but what will happen is that there is a shear lag effect you might have studied. So that will start to play a role uh, if your bolts are too far apart from each other. Okay, so that's why it limits it to 16 T or 200 mm. Okay, edge distances we had discussed 1.5 times the hole diameter, that is 1.5 times D0, or 1.5 times D0 or 1.7 times D0. I have not marked it here, but it's 1.5 times or 1.7 times based on what type of edge this is. So if this edge, the edge that I'm marking here, if this edge is machine cut, machine flame cut, or rolled edge, then you can be assured that this is a smooth edge and you can go for 1.5 times DO value. And if it is a hand flame cut machine or sheared edge, then there will be more inaccuracies in the smoothness. The smooth will be uneven, the edge will be uneven, and as a result, your edge distance has to be larger, and same thing holds true for the end distance as well. Okay, you understand the difference between edge distance and end distance, right? End distance is in the direction of the load. So if this is the direction of the load, this distance for this bolt, this distance will be called end distance, and this distance will be called edge distance. Okay. All right, moving forward. Now we'll get into the design of, yeah.
Sir,
Who is it?
sir, I have a doubt. This is Dhanush. I have a doubt. In the bolt properties table,
Yeah.
what is the exact significance of the stress under proof load when we have all the other stresses too?
Can you repeat? What is the significance?
Of stress under proof load values, because we have other stresses to deal with too.
Yeah, so basically, if you see the values here, these are taken to be slightly smaller than, if you see there is a ratio between this value and the proof stress. So for example, this value and the proof stress value, or this value and the yield stress value. Right? So basically it is, and that ratio is given by this one, right? 0.94, 0.91, this one. So basically what they are saying is that this is the proof stress level that you should try to achieve. These are the yield stress. These stresses are the yield stress or 0.2% proof stress. That is the material property. And what the code is saying, that you should try to achieve this level of stress, especially for these bolts. Not, it may not be applicable for all the bolts, but especially for 8.8 and higher bolts. This is the proof stress level that you should achieve through pre-stressing, pre-tensioning. Okay, and when it comes to actual amount of pre-tensioning, the other code is there which says, which gives the load value, and if you see, this load value are the minimum bolt tension. So this is the minimum bolt tension you should achieve, but this is the ideal proof stress, proof tension you should have. Okay.
Got it.
Yeah. Okay. Now moving forward. We want to study how to design bolted connections, right? So far we have understood different type of various considerations that are given thought to when we design connections. But there are what types of failures can we have? That is the first thing we should learn now before we get into the design. Okay, so one is the shear failure of bolts. So I am showing a picture of each of these kinds of failure. So this is how a shear failure of the bolt looks like, right? So this bolt was, what kind of shear was there in this bolt? Can you guess? Was it a double shear or single shear?
Single shear.
No, it was, to me it looks like a double shear. In one shear surface, it sheared very clearly, very significantly, and there is another shear surface forming here. So you can see this kind of a bulge shape, right? So you can see this kind of a surface forming. That means there is a shear plane here and there was a shear plane here. Okay. So this was a double shear kind of a bolt problem in which this bolt underwent shear failure. Okay, so one is shear failure. It could be single or double. And then you may have a bearing failure. So bearing failure looks like this, wherein the plate undergoes bearing failure. So the plate geometry deforms. You may also have bearing failure of the bolt, wherein what will happen is that just like the hole is changing its dimension here, so hole is becoming wider or longer, correct? In case of a bearing failure of the bolt, you have a round shaped bolt. You have a round shaped bolt. It's not really round. You have a round shaped bolt, and then there is stress acting on one surface. As a result, this stress will become flatter. So on this side, you will not see any geometry change, but this surface will become flatter as a result of bearing failure of the bolt. Okay. Then you have block shear failure of the plate and tension failure of the plate. Both of these you are already familiar with. These are not really bolt failures. These are more of a plate failure. Okay. So plate failures, you are familiar with them already, right? In tension members, you have studied them in detail. You have, right?
Yes, sir.
Yeah. So even bearing failure of the plate, in a sense, is failure of the plate, but you have not studied that so far. So that's why I'll be talking about it. And plus, it happens right at the interface of the bolt and the plate. So that's why it is important. It's part of this chapter. These three correspond to the bolt failures or types of bolt failure, bolt connection failure. Yeah. Out of these three, two are directly in the bolt: bearing failure of the bolt and shearing failure of the bolt. These are in the bolt, and bearing failure of the plate is in the plate. Okay. So you understood how these failures look like physically, correct? Now, as you may guess, if I may, which are the parameters which will control or dominate or have any role to play in the shear failure of a bolt? So if you are talking about shear failure of this surface, yeah. So which are the parameters? So there would be some material parameters, there would be some geometric parameters, right? So which parameter should those be? Which geometric parameter will play a role?
Sir. Hello?
Yeah.
Sir, can you once again explain the bearing failure of bolt?
Bearing failure of the bolt, right?
Yes.
So just like, see, for example, look at this plate. This hole was circular in the beginning, but because of this stress that was acting on this plate by the bolt, there were bolts here which was introducing a lot of stresses here, imparting stresses here, and as a result, this plate hole or bolt hole deformed to a new shape, correct? And there is a plasticization here. Similarly, you can see a lot of plasticization here. You can see it, right?
Yes, sir.
The material has deformed and increased in the thickness, but has deformed in the plane.
But it is on the plate, right, sir? It's not on the bolt.
Correct. So these are on the plate. Similar thing may happen on the bolt also. So to start with, a bolt will be circular. A bolt will have a circular cross section, but if you are applying stresses on this surface, there may be a case then that the bolt will become flatter like this. So basically this material on the surface may yield and it will get deposited on the sidewards. It will flow to the side, just like this one.
Okay,
Yeah.
sir.
So it will change its shape. Basically, it is a plasticization of the surface of the bolt. Just like this is plasticization of the surface of the bolt hole, this is the plasticization of the surface of the bolt. And it depends on whether the bolt is stronger or the bolt hole is stronger. So if the bolt hole is stronger, that is the metal, that the plate is stronger, plate is made of stronger material. In that case, the plate will not undergo bearing failure, the bolt will undergo bearing failure. And if the bolt is made of stronger material, then the plate will undergo bearing failure. Make
Okay,
sense?
sir. Okay, sir.
Yeah. So that is the bearing failure. Coming back to my original question, shearing failure. So which geometric parameters should play a role in determining the shearing capacity of a bolt? You can see here. So you have a plate. You have one plate here. You have another plate here, which are being pulled in opposite directions. And there was a common bolt which was connecting the two, and that bolt will have a shear surface, right? So which geometric parameter will determine the shear capacity of the bolt?
Shank area.
Shank area. Very good. So that depends whether the shear surface, the shear plane, that is the plane between the two plates, the plane common between the two plates, whether that lies in the shank portion or in the threaded portion. You understand? So you may have a bolt which that has a shank area, and then it has a threaded area. Okay. So the net cross section in the shank area is, let's say, I don't know what is the terminology for ANB, ASB. It is called ASB, and the smaller or the reduced threaded area, cross section area, will be ANB. Okay, that is A net B. Okay, so depending on whether that shear plane lies here or it lies here, whether it lies in the shank area or it lies in the threaded area, that cross section area, whichever it is, that will play a role. That is very good. So that is first the geometric property. Another one would be some material property will play a role, right? So here you should notice that you already know the location of failure. The location of failure is very confined, correct? It is not distributed. The yield plane, the portion which is going to yield, is not distributed over a length. It is already very, very precisely confined, and that is exactly the plane. For example, in this case, if you see, this is exactly the plane where the yielding took place, right? Or this and this, these are the two planes where the yielding or shear yielding took place. Okay, so if the situation is such that the deformations are very confined, then which type of limit state do we use? From tension member, you may remember there were two limit states: limit state of yielding and limit state of, what is the other one? Yielding and
Rupture.
rupture. Very good. So which one would be applicable here? If your failure is confined to a very small area, very small length rather than area, sorry, yeah, your failure is not distributed over the length of the bolt, it is confined to a very small, very narrow band, it is the rupture, right? Yeah. So just like you used to have in that case, so when you were having, let's say, a tension member, right? So a tension member's tension capacity is limited by two things: cross section yielding and net section rupture, correct? And why net section was considered for rupture and only the gross section was considered for yielding? The reason was that gross section rupture is very high limit state, so that we don't have to. Gross section yielding itself is bad enough. However, yielding of the net section is not a very bad news. Okay, so where the net section is, and why, what is so special about net section? The special thing about net section is that it is very confined, it is not distributed. Okay, gross section is distributed, gross section is same everywhere. So if it yields here, it will also yield here, it can also yield here, it can also yield here, it is distributed. The net section is at a particular location, okay, right outside of this one and right outside of, left side of this and right side of this, there is, the net section is not applicable, right? So net section is very well defined in narrow band, okay, and in that narrow band the net section exists, and that's why yielding is not a big deal there. Even if it yields, it will deform a little bit, who cares, that's okay. But as long as it does not rupture there, we are fine. So that's why we used to consider rupture of the net section. Similar thing would be applicable here, even though this is shear limit state. The planes where it is going to yield are very well defined. It is here, so that plane we may not know beforehand, but once the plates are placed around this bolt, that plane will be a fixed plane, okay, and only in that plane the failure can take place. So even if that plane yields, it's not a big deal unless it reaches the ultimate value, okay, because it even if it yields, it will deform a little bit, that's okay. But if it starts to plasticize too much and then achieves the ultimate stress, then there is a worry. So therefore, this is the expression for nominal shear strength of a bolt. And if you look at this expression, you have an Fu value, no, not Fy value, Fu value. Okay, and the reason for that is, as I have explained already, the planes. So these are the three plates here. So these two plates are being pulled in this direction, and this plate is being pulled in this direction. So you have a double shear situation. In this case, what may happen is one of the planes that is in shear is in the shank, but the other plane could be in the threaded portion, in the reduced portion. Okay, so then you have to take all such planes, the planes that are in threaded portion, add all of them, number of planes that are in, and S is the number of planes without threads. So N is the number of planes with threads. So number of planes that are lying in the threaded portion, that is NN, multiplied by the net section area at in the threaded portion. That is approximately 78% to 80% of the shank area. Okay. Similarly, you take an S number of shear planes in the shank where there is no threads. There are no threads. Okay, NS, and then the area of the shank, cross-section area of the shank, divided by √3. Why √3? Where does the √3 value come from?
One misses criteria.
One misses criteria. Very good. Okay, so this will give you the bolt shear capacity. Now this part is clear to everyone why we are not using Fy and we are using Fu. Can somebody repeat? Tell me back. What is the reason for using Fu rather than Fy for this limit state?
Because we are considering limit state of rupture due to the small area where the shear plane is.
Correct. Very good. So I don't have to repeat. Everybody followed it, right?
Sir, can you explain that once again, sir? Why FU, not FY?
Okay. All right. So the nature of this shear deformation or shear failure. Let's say I'm giving you a hypothetical condition that you had a long. Let's say I have a bolt, and I'm applying. It has a certain length here, and that length is significantly large in comparison to the diameter. Okay, and then I'm applying a force here, and I'm applying a force here in such a way that there is shear introduced in this one. In that case, I don't know where the shear failure can take place. Shear failure can, because the cross section is uniform from here to here, the shear failure can take place, shear yielding, that is, can take place here, 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 anywhere, right? And as a matter of fact, once one plane yields, it will go into strain hardening. So then this plane will offer more resistance, but the other plane will yield, and then the other plane. So basically, the entire length of that shank can yield in shear. It doesn't happen often because most of the times, in order to achieve shear type of failure, you have to keep the length very small. But I'm just giving you a hypothetical condition. Understood? So basically, as a result, the entire plane can yield, and what you will get at the end is this kind of a deformed shape. This is a typical shear deformation, correct? This is a typical shear deformation. If this was the case, the entire thing has yielded in shear, then you would take Fy. Okay, the reason for that is because if the entire length has yielded in shear, that means there will be a lot of shear deformation taking place. Okay, and you will lose the entire stiffness after a certain amount of deformation. The stiffness will be very, very low. So then in such kind of conditions where your damage is distributed over a length or can be distributed over a length, then you take Fy value, because Fy itself is harmful enough, is bad enough in such conditions, because you will get the bolt will not really rupture into two parts, but it will become so weak and it will deform so much then that the structure may not be usable. So that's why you limit it to Fy. However, in this case, what is happening is your forces are not acting this way. Even though the bolt is similar nature, similar length, similar proportion, but the way you are applying these forces are, imagine that you have some kind of a jacket here, which is represented by a bolt hole, and this is another jacket, which is represented by another bolt hole, and these two jackets are almost touching each other, and then you are pulling one here, one here. So as a result, what is happening? You are confining the damage zone to a very, very narrow band. Your damage zone is confined to this narrow band, right? Now, if you imagine the shear deformation of this bolt, it will be deforming like this in a single shear problem. The problem here is double shear, by the way. I don't want to draw the entire thing. That's why I'm showing it here like this. Okay, so in this particular case, what is happening, even if it is undergoing yielding, this particular plane where the shear deformation is taking place, even if it is undergoing yielding, the yield deformation will not be large enough, because not the entire length is yielding, only a very small length is yielding. So the yield deformation will not be large enough to make the structure unusable, and we can continue to use the structure. Okay. However, once this deformation becomes so large that it reaches FU value, then there is a serious risk of rupture, and that's what we want to prevent. So that's why the limit state is FU. Okay.
Sir, the
Yeah.
only difference between previous and now is like along the length it is confined here. In the previous situation where along the length it is not confined, so it is yielding uniformly throughout the length. Here it is confined except the plane, except that plane.
Yes, confined, or you can say the way forces are being applied. So in this particular
Okay.
case, if you see the forces, let's say it is being pulled this way, so forces are applied in this plane, and then here the forces are applied like here, like so. Okay, so
Yes.
the plane, the portion that is without any external forces is a very narrow band. So the entire deformation, the entire failure, yielding, damage, whatever you want to call it, will be confined to that plane only. Okay.
Okay, sir.
All right. So this will be the shear capacity of the bolt. Fu divided by √3. Why √3? Because this is shear failure. Ultimate stress shear failure. Nn Ns As. Okay. So this will give you the bolt shear capacity. Now we will also need to take a look at the bearing capacity. We'll go into that one first later. So let's say we already know the bearing capacity and we know the shear capacity. Then what we do is we take the minimum of the two. What is the capacity in bearing failure? What is the capacity in shear failure? Minimum of the two. That will be taken again. Once again. So I think I missed one step here. So first we get V and SB, which is the nominal capacity in shear. For that nominal capacity, we divide by the factor of safety, gamma, to get the design capacity in shear. This design capacity in shear. Okay, so VDSB is V, that is shear capacity, design capacity in shear for a bolt. Okay, now why are we saying shear again when we already mentioned V here? V already stands for shear, correct? Can somebody guess why? Why? What is the significance of this S while we are already saying V here? Okay, so this V basically corresponds to the conditions when the bolt is in shear. So we are not talking about the conditions when the bolt is in tension. When we talk about those conditions, instead of V, we will write T. Okay, so that is the meaning of V. So whether the bolt fails in shear or the bolt fails in bearing, in both conditions, the bolt is in shear. So that's why we are calculating the shear capacity of the bolted connection. That's what that V corresponds to. Okay, what this S corresponds to is this bolt shear capacity. Okay, I hope that makes it clear. As we go along, I think you will get to see it. Is that clear to everyone? Okay, right. So in addition to this, that is V and SB, there are some correction factors given for long joints, for long grip length, and thick packing plates. So if the joint is a long joint, what do I mean by long joint? Basically, when you have too many bolts or bolts are too far apart, of course, they have to be within the limits given here, whatever 12T or 16T and so on. But even within that limit, within 16T or 12T, whatever the loading condition, even within that limit, when the bolts are little too far apart or there are too many bolts, that will be called a long joint, and some correction factors are given in this clause, in these clauses 10.3.3.1, 10.3.3.3. Likewise, if it's a long grip length, which basically means is that this shank is bit too long. Okay, so let's say especially in this condition, if this plate is very thick, as a result, this bolt becomes, or the grip length is the distance between here and here, okay, between the washers or between the bolt heads. So that distance is a bit too long, and then you have this kind of a load applied. What may happen is that the bolt will not only be undergoing the shear failure, it will also be going partly flexural failure. Okay, and also if you have thick packing plates also play the same role, almost the same role as long grip lengths. So packing plates basically don't exert any force, so they can slide along with the bolt, and as a result they don't provide the kind of confinement you require to develop a very narrow shear type of failure. As a result, you will get some kind of a flexural kind of a deformation in the bolt, and that reduces the capacity of the bolt. And for such reductions, some correction factors are given. So I'll not be able to talk about those here, but I recommend that you go to these provisions and ask me if you have any questions. All right. The safety factor is taken as 1.25 as given in table number 5 for bolts. Gamma MB is given as 1.25 for bolts. Okay, irrespective of the failure mode. So whether it is a shear failure or is it a bearing failure, you have the same gamma MB value. Okay, so a bolt's capacity or a bolted connections capacity in shear is minimum of the two capacities. It's a shearing failure of the bolt itself, that is bolt shanks shearing failure, or bearing failure, correct? So this is the other one. This is bearing capacity of the bolt and bolt hole. So when you say bearing capacity of the bolt, we automatically mean that not only the bolt, but bolt hole may also undergo bearing failure. And both these provisions that we have talked about here are for snug tightened connections. Okay, if the connection is or if the bolt is slip critical, we had discussed this one in the last class. If the bolt is slip critical, that is, it is tightened pre-tension to the level where the plates don't slide against each other. Okay, if that is the case, then these capacities don't matter. What all that matters is how much is the friction available to hold the plates together, and whether that friction has been overcome under the force. So the capacity calculations will be completely different. Okay, these capacity calculations, bearing capacity and shearing capacity of bolt, that is bolt shear strength, both of them are applicable only when you talk about slip connections where the slip is allowed. Okay, or snug tighten, you can say. Okay, so moving forward, bearing capacity, nominal bearing capacity is without the factor of safety. So that is called VNPB. P again is basically a parameter that is called to represent B, that is bearing. Okay, so but instead of using another B, they are using P. Okay, VNPB. So P here stands for bearing. They might have found some another synonym of bearing to use instead of B, because they probably didn't want to use V and BB to confuse between two B's. Okay, so or maybe P is for plate, because plate bearing is much more common than bolt bearing. Bearing of the bolt is not that common, because most of the times bolt is stronger than the plate. So most of the times it is the plate that undergoes bearing failure, and that's why you have V and PB. Okay, now here, if I can go back here on this slide, which parameters do you think should play a role So this is a typical plate bearing failure. This is a typical plate bearing failure, right? So which parameters do you think should, geometric parameters first of all, should play a role in controlling the bearing failure of the plate?
Hole diameter.
Hole diameter, very good. So for any given force, if the hole diameter is large, and of course, if the hole diameter is large, the bolt diameter must be large as well, because there are limits to how much tolerance or how much gap you can have between the bolt and the hole. So of course, the hole and the bolt diameter, if they are large, then the stress will get distributed over a larger area, the same for the same force. Okay. So as a result, your stresses will be lower. So you are less likely to have a bearing kind of a failure. Good. What else?
Thickness of the plate.
Thickness of the plate. Very good. So because basically you are looking at the bearing area. Okay, so if I can mark that bearing area here, maybe I should use a different color. So if I can mark the bearing area here, this is that bearing area. You can see. So that bearing surface is basically the diameter multiplied by half, like diameter, or half the diameter multiplied by pi, multiplied by the thickness. So if you ignore pi, let's say that's just a number. So the parameters are diameter and the pi, diameter and the thickness. Very good. So these are the two geometric parameters. Material parameter.
Ultimate tensile stress.
Ultimate tensile stress of the plate, if you are looking at the plate's failure, isn't it? Because actually what may happen is you may be looking at the plate's failure, or you may be looking at the bolt's bearing failure also. So it is the, depending on which one is weaker, which material is weaker, you may have the failure of the bolt also, this one. Okay. Yeah, so ultimate stress. Yeah, so these are the three important parameters. Anything else that you can figure out from this picture?
Sir, why ultimate of the plate?
Why ultimate?
Why ultimate?
Why ultimate stress and not the yield stress again, right?
Yes, yes, sir.
Yeah, so again the same logic, because even if as soon as if you can, let me open another sheet. This is my bolt hole, and this is the bolt, and here it is coming in contact. So as soon as I apply force, what will happen is that initially there will be some yield, definitely, because to start with the two diameters are not same. How much area will be in contact if you have two circles of unequal diameters, one inside the other? How much will be the overlapping area? How much area will be common between the two, or will be touched? Over what surface area will this, or what arc length will these circles be touching each other? Santosh? Santosh had asked this question, right?
Yes, sir. Yes, sir.
Yeah. Yeah. Tell me.
Thank you.
Sorry. I have a straight line. I have a circle. If they are just touching each other, and the circle, of course, these are all very thin lines. So over what length does a circle touch the line? What is that arc length?
If it is line, it's just a point, right, sir?
Yeah, it's just a point. So zero length, right?
Yes.
Yes, exactly. So over zero length, that means the area, contact area, is also zero in this case. See, instead of a line, it's another curve. But even if it's another curve, the actual contact area in the beginning, when the two bodies are completely rigid, undeformed, you have a zero contact area.
Okay, sir.
Okay, even though they are touching over a line, but actual surface area over which it is touching, if you calculate that area, it will turn out to be very close to zero. Fine. So in order for it to transfer any force, it has to deform, it has to yield immediately, so that you can transfer some force. So this hole wants to move this way, this bolt wants to move this way, and for that to happen, this bolt has to deform a little and this hole has to deform a little. So some yielding has to take.
Yes, sir.
Okay, without any yielding possible, theoretically you cannot even transfer any force. So even at microscopic level, some yielding does take place. So yielding cannot be avoided. That is a given.
Okay, sir.
Moving forward, another issue is that this damage or yielding, whatever that wherever that happens over a very small area.
Sir, actually what you said, single point is only at the initial stage, but after throughout
I'm coming to that one, Santosh. Hold on. So after it has deformed the hole, let's say hole has deformed rather than the bolt deforming. So let's say the hole has deformed. So this is the part of the hole that has deformed and it is developing some stresses, yield stresses. Okay. So this portion of the hole has developed some yield stresses or is getting to the yield stress level or almost that. But still the deformations will be only confined to this band, this small narrow band. Okay. So let's say this length is anything like let's say the bolt diameter is 20 mm and hole diameter is also of the similar order, 22 mm. Okay, so for 20 mm, let's say this portion of yielding, where the yielding is taking place, is approximately how much? You can guess it to be 10 mm. Okay, so 10 mm length of the plate is yielding. Okay, all right, and let's say we are allowing it to go up to FU, and FU takes place at some strain level of approximately that is very difficult to guess likewise in this particular geometry, but let's say, see, yield point is epsilon y is how much? At what strain does the material yield typically?
0.0002.
0.2% strain. Okay, so if you say that I'm going to limit it to 0.2% strain, you are saying that 0.2% of 10 millimeter, that is the deformation value I'm limiting it to, so that there is no yield taking place. Okay, so how much will that be? 0.02 millimeter. Okay, that is a very, very small deformation for any real structural system, and then you are being overly cautious. However, if you allow it to go up to epsilon u, okay, and even when you do epsilon u, the entire length, entire 10 mm is not going to go to epsilon u. Only locally it will go to epsilon u, and soon the stresses will be, because if you do any finite element analysis, you can very easily see that the stress level. So this is the bolt hole, this is the bolt hole, and the stresses are distributed in such a way where the stresses right in this area are very high, but as you move away, the stresses become lower, and so these are the contours I'm plotting, stress contours. So stresses are lower and lower as you move away from here. So only in a very immediate neighborhood you would have some level of very high level of high stresses. So let's say at 10 times this strain, that is 0.2 mm, you will achieve something like epsilon u, ultimate stress. Okay, and that is okay. So 0.2 mm is not a bad news, and we are limiting it to FU value. So FU is the failure basically. So it should not go beyond the failure. Okay, and even if it goes under beyond failure, like it is about to approach FU, then we'll of course put the factors of safety and everything. But if you imagine, this is material in compression, right? So it is not a drastic failure also. Okay, so that's why, and plus 0.2 mm is not a very large deformation from any practical considerations. All right, so that's why it is allowed up to go up to FU and not limited to epsilon y or Fy. Okay, I hope I have explained this.
Yes, sir.
Yeah. So now here you see there is a D, there is a T, there is a factor 2.5, which is more like an empirical factor. You must have seen a lot of such factors being used in when you calculate the bearing capacity of a foundation in soil mechanics. You see kind of a effect is considered, and as a result, you calculate some factor, and some kind of factor is used. So such kind of factors are mostly empirical. These are not coming from the theory directly. So a factor of 2.5, which has, I'm sure, some effect of pi also included here. And then you have 4 different values here. Either you may have FUB, FUP, FUP E divided by 3d0 or FUP P divided by 3d0 minus 0.25. One thing everybody failed to notice here, this was a very interesting picture actually. I wish some of you had noticed this, was this shifting of or deforming of this edge. Now you must have noticed, right? So this edge is not straight anymore. It has deformed. And what does that mean? What it means is that closeness of the hole from the edge plays a role. So if, and that is kind of obvious, if if this hole was sitting right next to the edge or almost touching the edge or as close possible, as close as possible, then the bearing capacity of this hole will be very low, right? So the distance from the end matters, not so much this edge, but from the end it matters. Okay, and not so much from this edge also. So let's say the plate was only up to here and the force is acting in this direction, then this edge doesn't matter, this distance doesn't matter, but this distance does matter, right? So this distance matters. Also, if you have two holes in the longitudinal direction of the load, then their distance between the two also is important. Okay, because again the same thing will happen. This stress field will start interfering with this stress field. Okay, so that's why you get a parameter E here and you get a parameter P here. E corresponds to end distance along the bearing direction. Okay, E corresponds to end distance along the bearing direction, and P is the pitch distance along bearing direction. Yeah, so that divided by 3d0. So if E is equal to 3 times the diameter of the hole, then this factor becomes same as the plate bearing capacity. So basically, if your edge or end of the plate is at least 3 times the diameter of the hole away from the center of the hole, then you don't have to consider the edge effect or end effect. Okay. Similarly, there is a minus 0.25 also here. So you can figure out the pitch value. So the pitch is basically in the longitudinal direction. What is the distance between the two holes? So if the pitch is approximately equal to again 3d0, then you don't have to consider the effect of the pitch, effect of the closely located bolts. And like before, the design capacity will be equal to nominal capacity divided by gamma, just like before. Okay, and this provision is given in clause number 10.3.4. So now we have studied two types of limit states for bolts in shear. Anybody questions?
Yeah, but we already took care about the spacing and clearances in the before slide. Why?
No, those are the absolute limits. Those limits are absolute limits, so those should not be so close. So if you put the bolts closer than 2.5 times the diameter of the shank, that is not acceptable at all. Okay, and what this is saying is that you may have farther than 2.5 times the diameter, but if it is closer than 3 times the diameter of the holes, then there may be some interference that you have to account for in the bearing capacity. So if it is between 2.5 and 2.5 times the diameter of the bolt and 3 times the diameter of the hole, so these two values will be different, right? So diameter of the bolt is smaller than the diameter of the hole. So let's say you have 20 mm diameter bolt, so 20 multiplied by 2.5, how much is it? 50. So if it is less than 50, not allowed. More than 50, you may have it, and the hole diameter, corresponding hole diameter will be something like 22. So 22 times 3, actually it's minus 0.25 also. So you have to do that calculation. So whatever that pitch spacing is, you get. So you have some range in between where there will be some interference, and you have to account for it. Got it?
Yes, sir.
Okay. Moving forward, tension capacity of bolts. So there, as we had discussed, there were certain conditions when the bolts can undergo tension, right? So this was an straightforward possibility where you have some kind of a T section, structural T, which is being pulled and which is tied to a W section here through these two bolts. So these two bolts will be undergoing tension. And you may have various conditions where the bolts are undergoing a combination of tension and shear. This is combined tension and shear. All these bolts are similar conditions. Okay. So the image that I've shown here, unless this beam here is being pulled in the actual direction, in that case you would have direct tension in these bolts. Otherwise, if it is carrying any if there is any kind of a shear force or moment acting here, chances are that these bolts will be carrying some shear and some moment, or sorry, some shear and some tension. Agreed? So, but anyhow, we know that for bolted connections, tension can be very much a possibility, and we need to learn how to design bolts for tension also. Now, in tension, the behavior depends significantly between whether the bolt is a snug tightened bolt or a friction grip bolt. Because when you do a friction grip, when you tighten the pre-tension the bolt, basically you are introducing a tension, correct? But in a snug tightened bolt, you are not introducing much of a tension. You are introducing very small tension in comparison to the capacity. So we ignore the initial tension completely, and we just design it for the we just assume that initially tension is 0, and then we design that point onwards. Okay. Now, again, let's take a look at the geometry of a bolt that is in tension. So you have a bolt. You have the bolt head. I don't know what is the problem with this writer. It keeps drawing me this random lines. I have this bolt. This is the bolt head. And then there is a nut here somewhere. Okay, and the bolt terminates here. So this is a nut. This is the bolt head. And in this part, up to here, you have the shank. And then you have threads in this part. Okay. So effectively, if you now if I look at this bolt, and if it is in tension, what it means is that on this bolt, this head is being applied with some force here, right? And then this nut is being applied with some force here. Okay, and that is what is causing tension in the bolt. You agree? So the tension would basically mean that this tension has to be transferred through this length of the shank, and it also has to be transferred by this length through this length of the threaded portion. Now here you can very classically see the difference in the applications of FU versus FY. Okay, so now in this portion, where is the failure going to be? This is your threaded portion. Okay, so in the threaded portion, where do you expect the failure to be? The failure should be between in the reduced area, not in the gross area, right? Because the reduced area is smaller than the gross area, so failure should start from the reduced area. Whereas in the unthreaded portion, You guys are following me, right? There is suddenly complete quietness. It's better that because I tend to forget to check the messages, you can unmute your microphone and reply. That might be more convenient. So if the tension failure has to take place in the threaded portion, it will be in the reduced cross section. And if it is to take place in this unthreaded area, that is shank area, then you have got the gross cross section. That's the only thing available. Okay. So as you had done in tension members, the failure was determined by the yielding of the gross cross section and rupture of the net cross section. So you were using FU at the net cross section and yielding of the gross cross section. Then you were using two different factors of safety, one for the rupture and other for the yield limit state. Gamma MB, as you have seen, is 1.25, and gamma M0, you are already familiar with, is 1.1. Okay, so now, and then in addition to that, we were also using in the rupture limit state, you may remember, we were using a factor of 0.9. This 0.9 correspond to the drastic consequences, catastrophic consequences of a rupture. Okay, yielding of the shank may not lead to a catastrophic consequences. It will just make the connection unusable, and you may have to replace it. Right, so you don't want that to happen. But even if it happens, it does not lead to a catastrophic failure of the structure. But a rupture of a bolt may lead to catastrophic failure. That's why you want to add additional factor of safety, that is 0.9 added here. Okay, so that is the bolt design in tension is exactly the same as any other member being designed in tension. The only thing is for the net section, for the bolt, you take the reduced cross section of the net tensile area, that is area at the bottom of the threads. So at between this point and this point, that is the reduced cross section, that's the area you take. Okay, is that part clear? All right, guys, so I think I can stop here. We will continue discussing priming action, which also happens for in tension conditions. We'll discuss in the next class what priming action is. Anybody has any questions?
Sir, in none of these cases, we consider the diameter of the head of the bolt. Is that because we are considering a snug tightened condition?
In none of these, you mean in the shear capacity as well as the tension capacity?
Tension.
In tension
both
only.
The cases, we don't. In both the cases, sir, we don't consider the diameter of head at all because that might affect the influence area.
Yeah, I think that is a very insightful question and will lead to a very long discussion. Basically, what happens is that when these bolts are designed, the way standards are developed, so when they specify, they always specify for this much of shank, for this kind of material, you have to have a head of this size. Similarly, there are many things we have not discussed in the ways a bolt can potentially fail. So let's say if I ask you to make a bolt of your own, okay, or if you ask me to make a bolt of my own, I'll make so many things. I'll can like if I don't have experience and if I'm not familiar with those codes, I can design a bolt which will fail in ways which are not covered in the code. And the failure ways that are covered in the code are assuming that the bolts are already standard. That means, for example, what guarantees that these threads will not fail? So I'm never going to talk about the failure of the threads, right? There is a very much a possibility that you have a bolt and then you have a thread, then you put a nut through the threads and you apply the tension. And I'm saying, okay, the shank is going to fail, the threaded area is going to fail. How about the threads themselves? The threads themselves can strip off. You understand what I mean by threads stripping off?
Yes, sir.
Yeah. So you have these threads in this bolt, and if I'm applying through the nut, I'm applying this very heavy force on these very small tiny areas. Yeah. So the contact area here is very small through which this force is getting transferred. And you can experience this thing in a lab or something. Let's say you have some 7-8 threads, or the nut is 7-8 thread wide. So this is your nut, which has some 7 threads or something. Let's say you tighten only 1 or 2 threads, and then you apply the entire force. You will see that before anything else happens, the threads will fail, and the nut is not usable. The bolt is also not usable because your threads have died. They have completely become flattened. So why aren't we considering that? Because when they design these threads, so how deep these threads should be, how many threads should be there, or in other words, what is the width of the or thickness of the nut, all these things are already standardized, which take care of the possibility of other types of failures. Similarly, there may be a failure when, let's say, you apply tension here. There is a very good possibility that this head ruptures off here. Okay, but before the rupture, the head would rupture off, you are going to have a yielding of the shank here. Correct? So that's why head's rupture cannot be considered. There is a good possibility that the head can shear off here. So if you imagine you have this bolt, you're applying a force here, and so this is how the forces are being applied on a bolt in tension. So this is your bolt head, right? And this is the shank, and shank is being pulled in this way, and the head is being pushed that way. There is a very good possibility that you may have a shear surface developing here, because this force is effectively getting, if you imagine that this shank is continuing, of course this is a monolithic material, but you can imagine the way you want to divide it. So basically what is happening is that this shank is being pulled this way, and at the head location it is being pulled this way. And if you can imagine the head as a separate body, then this head is being pulled this way, bolt head. Okay, so this is the shear plane you are getting here, and there is a shear failure possibility. But when you design a bolt, you make sure that these things don't happen. Okay, so that nothing inside the bolt will fail on its own. Only when you apply too much of force, the entire bolt can fail, and only these two types of limit, or 2 or 3 types of limit states are possible. Everything else is stronger than these. I hope I answered your question, right?
Yes, sir.
Okay. Anything else? All right. So now we can stop here today, and we'll continue. I think tomorrow we have a class at 10 a.m.
Yes, sir.
Yeah. So tomorrow we should definitely complete this topic of bolted connections, and I hope to start some discussion on welded connections also. Thank you.